Last section of this chapter is operations of functions. Oh, by the way, if you want to do any review exercises, I did post the student solutions for review exercises on the web. So if you want to practice, say, graphing a piecewise function, there's some examples you can do. Anyway, does anybody know ahead of time what type of operations you can do with functions? By functions, I mean, say you have two functions, f of x and g of x. How can you combine those two to form a new superpower function known as h of x? You could add, you can subtract, multiply, divide, power. Ooh, f of x, g of x, like this? Nice. Yeah. Anything else? Who? G of f of x? That's the composite function, right? G of f of x. So there's lots of ways of combining the functions. In fact, there used to be a section we had to graph based on the operations of functions. In case you didn't know it, you can add, subtract, multiply, and divide that we just talked about. The one thing that you need to know, and it's pretty obvious, is the domains pretty much stay the same whether you add, subtract, or multiply. When you divide, obviously you have that dividing by 0 possibility. That's going to change the domain of your function. If you have two polynomials, f and g, it's known as a rational algebraic function when you divide. But other than that, the domains are pretty straightforward. I just figure them out as is. Okay? So yeah, you can add, subtract, multiply, and divide like variables. So with that said, I kind of missed my mark, but here we go. I'm not going to do all these. I think it's just notation. In case you were ever to take an aptitude test like on Monday to see if you know anything about algebra. Let's just do like A and C. So how do you think you would do f plus g of 3? There's actually a couple ways you can do it. Yeah, put 3 into both of them, then add them. You end up with -9 plus 5, -4. The other way is to take the variables, add them, and then subtract. Sometimes it's easier with the variables, sometimes it's easier with the numbers. And then you put in 3, you end up with -4. Okay? That's not too difficult. I'm looking for a composite. I don't see one on that page. So, and you do the same thing with multiplying. You can multiply the numbers together, or you could multiply the expressions together. But again, that's pretty easy. We're not going to spend a lot of time on it. We got bigger and better tasting fish to fry, so to speak. -45, -45. Okay, then you put the 3 in. Right, but you can do all that stuff. And, it should be pretty easy when you go through it. All right, let's get to the composite. Add, subtract, multiply, and divide. Find the domain. Anybody have any domain issues we need to talk about before the test on Thursday? The only one that would be difficult, I think, would be f divided by g. The square root of 3 minus 2x over the square root of x plus 4. The domain would be the intersection of both domains. In other words, what do both domains have in common? What's the domain for the numerator? Well, 3 minus 2x has to be greater than or equal to 0, right? It has to be a positive number or 0. So what makes it equal to 0? Yeah, 3 halves. And this is the negative and this is the positive region. You put in 0 and it's positive, put in 10 and it's negative. So it's everything this way. And for the numerator, how'd you do that one? Yeah, same thing, except it can't equal 0. So what makes it equal 0? -4. This is the positive, this is the negative region. So that turns out to be open circle with a line going this way. And whenever you put functions together, the domains are the intersections, especially with a quotient. So by putting it together, it'd be from -4. That's kind of cool. I actually did just kind of put it together. It'd be from -4 to 3/2 with a bracket. Make sense? I can't tell what you know and what you don't know because some of you are just kind of like not really back in the swing of things yet, or thinking about calculators where they are. All right, -4. Questions on that? I don't think we need to go through the adding, subtracting. They're all pretty much the same, except to probably have a bracket over -4. Okay. Oh, a composite function. What type of diagram is this again? Yeah, it's a Venn diagram. And I don't really think of it like this. Some people do. You have the domain of G and the domain of F, and we put them all together. You can come up with a domain. I just put together and see what I come up with. The main thing about this slide is this is the outside function, and this is the inside function. So that's why it goes inside the parentheses of F, which just goes outside. The order matters on this from left to right. The outside function and the inside function. So that matters. And that's a composite function made up of more than one function. If you look at it, though, any function could be a composite function you've ever thought about, ever. You can think of it as a composite function. Like, for instance, this is kind of like, I don't know. What's your favorite function? Somebody in your row. You can either pick or pick somebody else. Hannah, what's your favorite function? Just pick any function with numbers and letters. Three x plus 2. Okay? That could be a good function because you could let g of x equal x plus 2 and let f of x equal 3x. The other way around. Sorry. So, if I do it the other way around, the outside function f of x would be x plus 2, and the inside function would be 3x. So I'm going to take this, if I'm using my rule f of g of x, and put it in for that function, and you get 3x plus 2. You're taking one function, putting in for all the variables of the other function, just like you do with numbers. Okay? Just like you do with numbers. It's the same thing. Let's do some examples. These are fun. These are my favorite ways of combining functions. F of g of x. F of g of x. So this says I have to take the g of x function and put it into all the x's of the f function and simplify it. Okay? I think you've done composite functions before, as I recall. This is just kind of like a review before we get to the test. And for today, we'll leave it like that, but usually you multiply it out. And the neat thing about this is, when you switch g of f of x, you obviously get a different answer. Now I take the f function and I put it into the g. So I'm taking this whole thing and putting it into this x. So I have 3x squared minus 1. What happens when you put in, let's see if you remember. What happens if you put in f of g of x, and that equals the same thing as g of f of x, which equals x. Do you remember what that is? Well, not only are they the same thing, but they both equal x. Okay. Anybody? I'm like leaving the floor open here for an extra 30 seconds. Oh, that means F and G are reciprocals of each other. Not reciprocals, inverses. Inverses of each other. Like, you know, inverses. Like the inverse of x squared is the square root of x. Not reciprocals, inverses. Like the inverse of addition is subtraction. There we go. We're getting Sean, see? All right. Let's go down here. Anyway, that's just a little math fun fact for the day. We'll worry about inverses later. This section, I think. Do you have the idea how the composites work, or do you remember how they work? How about g of x? G of x. X minus 1 goes in for all the x's of g. X, parentheses, x minus 1 minus 1. Okay? Yep. Yep. All right. Well, let's move on. I don't want to do any more. Here we go. I want to do values. Do C and D on your own, and I'm going to do them. There we go. Got it. Oh, that was even a bad cast, and I still got it. I'm going to scroll down and give myself some working room. All right. You do C and D on your own. And I'm going to see how you do. It doesn't matter what you got. It matters what you got. All right, what'd you get? In the back, what'd you get? What'd you get for D? Huh? Anybody else get 47? Anybody get anything different? Only 5 people got the answer to this question. Oh, still working on C or D? D? Let's see. G of negative 2. 4 times 4 is 16. F of 16. 47. I'd buy that one. F of 3 equals 8. G of 8 equals 64 times 4. Sounds good. Nice job. Questions? Excellent. Nah, we got those. All right, here we go. Got to find the domain. My slim piece of advice on this is when you're working with composite functions, you find the domain at the beginning, not at the end. You find the domain at the beginning, not at the end. Some people simplify way too much, and they get the wrong domain. And then they get very upset. But for part A, it says f of g of x. So that means g is the inside function. So I'm going to put in x squared plus 2x in for this x right here and subtract 15. There is, I'm not going to simplify, I'm not going to do anything, because I'm just looking for the domain. And my feelings are getting hurt when I'm grading papers. A lot of people aren't getting these domain questions with the radicals right. I don't know. I guess it takes a while, but I guess I explain it so everybody does it the same way. How would you do this problem? Yeah, set it greater than or equal to 0. When you take it, it has to be non-negative. I don't know how many times I've done this and people have taken and done some other things, but I don't know, maybe they're just trying out a postulate they want to become famous for. X plus 5, x minus 3. What numbers are they? Yeah, negative 5 and 3. You could have got that from the quadratic also, but it doesn't tell you which region you want. You know, if you put in a test point 0, that's a negative region, and these are both positive regions, I believe. Negative 10, positive, and 10 would be a positive. So which regions do you want? Yeah, and it can't equal because it says or equal to. So you just write the domain in interval notation. Negative infinity, negative 5, union 3 to infinity. Now, I am going to do the second part because you're going to see the difference between the two. G of f of x. This is the most common mistake. Oh, any questions on that? We've done a bunch of inequalities, so. G of f of x. See if I can remember this. G of f of x. So that means I want to have something squared, which is a square root of x minus 15 plus 2 times the square root of x minus 15. Here comes the faux pas, you might say, when it comes to composite domains. Some people square this, then they find the domain of that result. That's not how composites work. Composite works from the very first time you combine them, what's the restrictions? Well, in this case, obviously, x has to be greater than or equal to 15. Even if you squared it or simplified it, you got x minus 15, that doesn't change the domain of the function. You have to look at it as is when you first start. Don't get the domain of a simplified composite function. Get the domain right away, and then that's the domain for everything else. Well, you're lucky in this case because that doesn't simplify the second term, but the first term does. Just don't let yourself fall into that trap. So you just write 15 to infinity. Okay? And then that's, I mean, we could go through this, but I don't think I need to. And as soon as I don't, someone's going to say, I didn't. There we go. 15. Got it. Why don't I ever take the 15 to the other side? Well, I think it was this class that half of you forgot to switch the inequality when you divide it by a negative. That's why I never isolate it and divide by x. The number, I always go with factors. I hate that division by a negative on the inequality. I used to miss it, but not anymore since I went to factors. Okay? Fantastic. You want to do another one? You get the idea. You got the idea? Yeah. All right. Let's do one more on your own. B. G of f of x.
The domain or both? Like find that.
No, yeah, no, just find the domain. G of f of x. Give that a shot. Did anybody ask themselves a conceptual question first?
I don't even know what that one means.
Conceptual? Sure, it's a concept, it's an idea. We all know this. Is there any time, here's an example of conceptual question. I try to ask them a lot. Is there any time the square root of 3 minus x is going to be like negative 3? Is there any time where this is going to equal negative 3? No. The statement saying, where is this going to be positive at or equal to 0? Well, it's never going to equal 0, is it? Because the square root's never going to equal negative 2. So based on that school of thought, you can just say, okay, next one is, where is that going to be true? Oh, not the square root, but just the 3 minus x. And whenever I do this, people always say, well, where did the 2 go? Well, it didn't go anywhere, but you know that 3 minus x has to be a positive number. That's your next thought. So you kind of solve it conceptually instead of algebraically. Does that make sense? There's really, the only reason the plus 2 is here is to make sure it's positive in case this will turn out to be a negative 2, and that's not ever, you're not going to square root something and get negative 2. So that's basically thrown out. So I can see that x is going to have to be from negative infinity to 3, right? Anybody get that? Half the room? Okay. Does the explanation make sense, or does it sound a little hocus pocus? Yeah? Mm-hmm. Yeah, it is. You want to try part A? Part A is a lot tougher, yeah?
What if it was a 4 there instead of 2?
A 4?
Yeah.
Well, there's no way the square root's ever going to be a negative number, so whatever I add to it's always going to be positive. The smallest this number can be is 0. In that case, 0 plus 4 is still a true statement. So I don't have to worry about this number at all. I just have to worry about this being positive. Now on the flip side, if I go f of g of x, if I have this, the square root of 3 minus the square root of x plus 2. Now we have some problems. Do you see how now you're subtracting radicals? And you have to maintain that being positive. Is there any number you can put in for x in this case where it will come out to be, where this will come out to be negative? Yeah, there's lots of them now. When you're adding a square root and a positive number, that's always going to be a positive number. However, when you're subtracting a square root and a positive number, now you have the potential problem of getting a negative inside the radical. 3 minus the square root of x plus 2. Same strategy, I just rewrote it. Now I'm going to ask myself, is there ever a time where this could be 3 or higher? Well, sure there is. So this number has to be what? Less than or equal to 3? Does that make sense? So now I know I have to have x plus 2 has to be less than or equal to 3. To make that a true statement, right? Is that right? Well, if this, okay, this number comes out to be 5, 3 minus 5 is a negative number. That can't be. So when would the square root of x plus 2 be less than or equal to 3? When would that be true? Well, whenever x plus 2 is less than or equal to 9, right? Right. 7. And it'd be a closed circle going this way, because that'd be the negative region, that'd be the positive region. Yeah. -3? I don't know. I know, so if I put on like -10, that wouldn't work, would it? So not only does this expression have to be less than 3, greater than -2, I'd buy that. It'd be from -2 to 7. See, that's a lot tougher problem when you're subtracting inside the radical than when you're adding. There's a lot more to keep track of. Yeah. Right, it can equal -2. If I put it in 7, it's going to be bigger. Oh. That one was fun. I don't think there's anything like that on your test. Has anybody looked at the practice test yet? Okay. I don't think there's anything like that with a composite on there. Oh, how much time do I have left? Oh, good. A lot. I like it. Well, let's try B on this one, see how we do, see if we need to do A, okay? Again, finding the domain means putting it together and coming up with something. F of g of x. I don't think this one's nearly as difficult. Denominators aren't nearly as difficult as radicals. Radicals are the worst. So, g of f of x. We'll try B again. That means g of f of x which means I'm going to put in f of x for all of x. All right, I think I got it. 1 over x minus 1 minus 1. Oh, that's an easy one. What's the domain of that one? What? Yeah, union. With what? Negative infinity to -1, or to +1, right? It can be anything but 1, basically. You can get a common denominator if you like. But I think we're good on that. Ready? Yeah.
On that one, do you set it like greater than or equal to 0?
No, I just put that x minus 1 can't equal 0. So x cannot equal 1. It can equal everything else. Okay? All right. I think we're going to save the rest. We'll do one more. Just because I like this question, we'll save those for tomorrow. But I like this question a lot. It's where you don't have an equation, but you have tables. I know. I like tables a lot. So you have to find the value of t of s of 1 using it. It's kind of like a game. I like this game. It's a logic game. It's in your book. Several values functions are given. It's kind of like that game I saw on TV. I was walking by, and they go, what would be extinct if rhinoceroses ruled the world or something like that? They were playing a game, and I didn't understand it. I don't know. It could have been. And the answer was Danishes. There you go. See? They were playing a game. I didn't understand the rules. I heard the question. I go, whatever. I just kept walking. So on this one, the rules are you're given two functions. T is one function with a variable t. The other one is S function with the variable x. So the idea is you take 1 through the S function, you find that answer, and run it through the T function and see what you get. Based on the possibility of typos, there might not be an answer. So if I take 1, see, a lot of people go, ooh, there's a 1. Well, no, that's not. This equals S of 0. See how that works? This equals S of 1. That's what you want. S of 1 equals 0. Woohoo! So now you have T of 0. So I go to 0 and I get 2.
This is fun.
It is kind of like code. I like that. Okay? Like, don't forget to drink your Ovaltine. Okay?
Or what?
Ovaltine.
What's that?
Never mind. Ready? Try S of T of 1. I have 3 more questions for you to do today. These are 2 of them. That's a surprise. S of T of 1. I don't know, is it? T of 1 is 3. S of 3 is 2. All right. So S of 3, that equals 2. So ours are good? C is what? 0. I don't know. T of 1 gives me 3. T of 3 gives me 0. Perfect. I like that. That is math. That's logic. That's a conceptual question. All right, here we go. Your last question of the day.
That was the last question.
No, I said you had 3 questions. 2 of them were there because somebody there goes, what's the third? I said it's a surprise.
Because there is none.
It is. It is.
Question of the day. Whoa.
Thank you. They do. You would think. Perfect. If P over Q equals 3 and P plus Q equals 8, then what does P times Q equal in quiet, please? Take just a minute to come up with this. If P over Q equals 3 and P plus Q equals 8, then P times Q equals blank. You might have to write something down.
Thinking, I'm trying to figure out what to do.
Thinking is best done when you write.
Right.
When you write.
Right. So,
Did you get it?
yeah, it
Nice job.
took me a second.
You did? All right. Who did it what? How'd somebody do it? Yep. For the what? Yeah? 1 and 7, 2 and 6. Oh, then 6 divided by 2 is 3. So 6 times 2 is 12. Nice. Anybody have a different idea? Yeah? That's okay. Okay.
That was the first thing I was thinking. Then I realized that.
So that means P equals 6. And 6 times 2 is 12. Good. Different ways of looking at the same thing. I like that. Does anybody else do it a third way? No? You missed it? That's all right. All right. For the homework, try to get through page whatever 1 through 39 odd. 196, thanks. Test Thursday. All right, we'll do homework questions tomorrow. All right, I'm going to shut this off now.